Hello everyone, I'm Abhishek and I'll be presenting my project on MeshGraphNets, which I did for my course of computer graphics over spring 23. So MeshGraphNets is basically a machine learning model that learns the different representations of meshes, and it is able to perform physics-based simulation without having to without having a simulation solver in the loop. That is, it learns the it sort of learns the physical equations, and without having to actually solve them, it knows what's the value of a particular node, for example, the position and the velocity at a different time step based on its training data. Uh, so, so let's go over some background. There have been many works that have tried using machine learning to learn the representations and the physical equations of a dynamical system. The following four on the screen are key notable papers that have influenced a lot. First, learning particle-based dynamics for manipulating rigid bodies, deformable objects, and fluids. In this paper, the author have assumed all the solids and liquids as a collection of particles with different forces amongst each of the particle, and have used machine learning model to learn the interactions amongst them. Then is the Lagrangian fluid simulator with continuous convolutions. In this paper, the authors have used continuous convolutional neural networks to learn the diffusion and the advection equations for fluid simulation. Then comes the learning to simulate complex physics with graph networks. This paper introduces graph neural networks in a framework known as graph network simulators, which learns to simulate the physical systems by updating and iteratively refining the graph state based on the current state and the learned dynamics. And finally, graph networks as learnable physics engines for inference and control. This paper introduces another sort of architecture called graph network dynamics, which again uses a graph neural network to learn the underlying physics of different objects. So going over the architecture of GraphNet, let's assume that we have a system of different balls connected amongst each other with springs. Now, the first thing that we do is a phi e operation, which is applied per edge. So in our springs example, this might correspond to the forces or potential energies between the two balls connected. Then what we do is we apply the rho e to v aggregator. This function aggregates the edge updates for edges and projects that into the vertices v. So in our running example, this might correspond to summing up all the forces or potential energies that are acting on the ball. Then comes the phi v that is applied onto the node itself, and which calculates the node attributes. In our example, this may compute something analogous to updated positions or velocity and kinetic energy of each ball. Then we apply another aggregator, which aggregates the different embeddings from different nodes, which is used in a global update. This may be thought of as computing the summed forces which correspond to Newton's third law in our example. And finally, we apply our another final transformation of which is rho u, which is applied once per graph, and it is analogous to something as the net of forces and total energy of the physical system, and equating that to some constant value. In the MeshGraphNet paper, we do not use the transformation rho v to u or phi u. That is, we do not use the complete. Rather, what we simply use is phi e, edge transformation, phi v, node transformation, and aggregator rho e to v. Now, this whole thing happens in a three-step process. First is the encoding, as you see here and here. Both of these neural networks take in edge and vertex positions. And what they do is they convert the positions and the respective attributes into some sort of embeddings. Next comes the message passing step, which happens inside this big block. The message passing steps can be thought of as aggregating the various embeddings from either the edge or the nodes and updating those embeddings. And as the number of message passes increases, we can think that we are getting k hops away information from the node. For example, if the number of message passing steps is 2, it means each node will be getting the information of other nodes which are 2 hops away. So finally, once the different message passing steps have been executed, we come to the decoder step, which takes in the node embeddings and gives out the node positions and attributes for the next time step. So before we know more about the modifications that I have done, we have to know what is a sender and a receiver. So for any graph, for any mesh, in our case, I can consider each of the edge as a bidirectional edge, one from node A to B and one from node B to A. So for an edge coming from node A to B, A would be the sender while B would be the receiver, and vice versa for the case of the edge B to A. So coming to the original paper, for the function of phi e, what they had done was they had simply used a neural network which collected the attributes from the sender and receiver nodes and applied a neural network on top of on those aggregated concatenated node embeddings and updated the features of the edge respectively. Then for an aggregation for calculation of node embeddings, that is for rho EV function, what they did was they simply summed up the different node embeddings for one particular node, receiver node from various from all of its neighborhood, whichever were connected to it, and simply summed those up. And finally, the updated node embeddings were calculated using another neural network. The modification that I did was I added attention to this process. Now, attention can be added to the model with help of two variables, I would say, a scalar variable alpha and a vector variable beta. Alpha takes in the values from sender, the node embeddings from sender and receiver, while beta only takes in the values of sender. And finally, the aggregator function, instead of simply being a summation of edge embeddings, it's a weighted summation of those those embeddings. Now, how are these alpha calculated and beta calculated varies from attention model to attention model. In my case, I have used 2 attention models, self-attention and vertex attention. So in self-attention, alpha is calculated using a dot product of neural network NN alpha, which takes in, we can assume that this is the query neural network. And while the neural network NN alpha key takes in the receiver's, the sender's node embeddings, while NN alpha query takes in the receiver's node embeddings, and it calculates a dot product and uses exponential function to get the weight alpha e for that particular pair of sender and receiver. To calculate the beta, it simply uses a neural network, another new neural network, NN beta, which takes in the sender embeddings and calculates a new vector. And finally, the new node embeddings are calculated using a neural network which only takes in the updated edge embeddings. It doesn't take the concatenation of updated edge embeddings and the node embeddings as was done in the original work. Now, in vertex attention, what we do is the alpha is again calculated with help of sender and receiver networks, node embeddings. But instead of doing a dot product, what we do is we calculate an Euclidean distance between the two before using the exponential function. Next, what we do, the values of beta is calculated similar to the self-attention network. And finally, the new node embeddings are calculated using the original model's way, that is using a neural network which concatenates the updated edge attention, the updated edge embeddings and the older node embeddings of the current state. So what's the experiment? In the experiment, what we have done is we have taken a rectangular piece of cloth which has around 1600 nodes and 3.1K edges. We have a training data from a actual physics simulator of 400 time steps while a wind is being blown on the cloth. The vertex attribute that I have been talking about all this while is basically velocity x, y, and z at each of these node points, and that has been concatenated with a one-hot vector of the type of node of that particular instance. For example, the nodes which are connected to an obstacle would be obstacle node, while a normal node which is a cloth node, can be would be a normal node. Similarly, the edge attributes that we have been talking about is basically XYZ, that is the world position, the norm of world position, UV, which is the mesh position, that's the location of our node in the mesh, and the norm of mesh positions. Now, we have trained our all the models for approximately 10 raised to 6 machine learning time steps. Our test data is running the learned model for 200 time steps, and then checking the values of the world positions of each of the nodes for the 200 time steps, simulation time steps. Now, results. So when we train only for 10 raised to 5 time steps, we see that both the attention models are outperforming the original model by a huge margin. As you can see, for a rollout of 200, the vertex attention model seems to be outperforming the original model by about 1500%, while the self-attention model is outperforming the normal model by around 300%. And the second table shows the actual values of the mean squared errors for different rollout time steps. Now, this video shows the various visualizations of the rollout at different after training for 10 raised to 5 time steps, as 10 raised to 5 machine learning time steps. As you can see, vertex attention model gives the best output, which was indicated by our error results. Original model is definitely not good. However, our self-attention model, apart from the nodes which are connected to the obstacle, the normal nodes seem to behave better than original model. Now, what happens when we completely train for 10 raised to 6 time steps? Here, we do see a change in the output. That is, normal model seems to outperform the self-attention model, but the best model is still the vertex attention model. This time around, the vertex attention model is about 15% better than the normal model, while the self-attention model is 10% worse than the normal model for at 200 time steps, rollout steps. We can see in the rollout visuals that, again, the vertex attention model performs the best, while for original model, we do seem to have certain artifacts in the simulation, and that is also visible for our self-attention model. So, though there seems to be significant improvement in the mean squared error after different rollouts with addition of attention, however, the cost of training has also increased significantly. So to give you in numbers, when I trained these models on an NVIDIA Quadro RTX A6000 that's provided by TAMU HPRC, the original model took around 21 global steps per second, while the self-attention took only 8.65 global steps per second. And the vertex attention model took about 9.8 global steps per second. Now, what that directly translates to is the original model took 1.5 hours for training 10 raised to 5 steps and 13 hours to train 10 raised to 6 steps. The self-attention model took 3.2 hours to train 10 raised to 5 steps and 32 hours to train 10 raised to 6 steps. And the vertex attention took 2.8 hours to train 10 raised to 5 steps and 28 hours to train 10 raised to 6 steps. So that's a speed up, or speed up by 0.5, I would say, or rather, I should say, a slowdown by 2x compared to the original model. So concluding this, my preliminary testing shows that attention models are great. They are definitely giving out significant improvements over the original model. However, this happens at the cost of longer training time. There are tons of things that we can do to confirm if attention models are indeed better than the original model. Some of them are, first, as we see, the gap in the original model and attention models seem to be decreasing as we increase our training steps. Thus, we have to train all of the 3 models to more time steps to see if the gap further reduces. Next, the authors in the original model claim that their framework generalizes to much larger testing meshes. Thus, we have to see if attention models also are able to generalize. So bookkeeping and explanations, I will be posting all the video links to the explanation in this particular part of the web page. The code of all the above models can be found in my repository. And the code and how to run those code can be found in DeepMind's GitHub repository given here. Thank you, everyone, and have a great day.